Alright, so last time we found that if we want to calculate the slope at a particular point along a graph, then all we have to do is we have to calculate the limit as h goes towards 0 of f of x plus h, and that's the little bit of height that we've got, minus f of x divided by h. And we found that we can consider a point on a line at f of x and then f of x plus h, and we can consider this to be the rise, and then the run is going to be h. And as h gets smaller and smaller and smaller, we get to the point where we approximate the slope at that particular point. And so we can either denote this as f dash of x, and then this here is the derivative of the function with respect to x. Another way you might see it, which kind of ties in with this this fact that we're getting smaller and smaller amounts of rise and run, is df dx. And this d means a small change in. And so before, when we had a line, we had delta f divided by delta x, because we could pick any 2 points and calculate the difference between those. But in terms of more complex functions, we have to think of infinitesimally small changes in f. That's what this bit is called, and we divide that by infinitesimally small changes in x. And so along a function here, at this point here, there's going to be a very, very small rise and a very, very small run, and we're going to calculate the slope from that. And we can just use this equation here, plug in a function, and we can work it out. And there are lots of different functions that have been calculated for us. So, for example, if we have a polynomial, we can find out that if we want to find the slope of a polynomial, let's just take the parabola that we showed earlier, and I'll just prove that if you have a parabola that's of the form x squared, f is equal to x squared, that this actually gives us a line, which is what I said, but I'm going to prove now. So what I'm going to have is I want to calculate f of x plus h, and that's going to be equal to x plus h squared. So I've replaced the x here with x plus h, and my f of x is just simply x squared. And that's going to be divided by h. So let's go f of, so we're going to have x plus h squared minus x squared. And that's all going to be over h as the limit of h goes to 0. And this is going to be our f dash of x. So let's expand this out. So we're going to have x squared plus hx plus 8x plus h squared. And so we're going to have x squared minus x squared divided by h. And so we're going to have x squared plus 2hx plus h squared minus x squared divided by h. And you'll find that that x squared and x squared cancel, and so we're left with 2hx plus h squared divided by h. And so let's look at the limit of as h goes towards 0. So as h goes towards 0, this number here is going to get smaller and smaller. This is also going to get smaller, and well, this one's going to get smaller probably the fastest, so that one there is going to go away. And then we've basically got 2h x over h, so the h's will cancel, and what we're left with is 2x. And actually, what helps is putting in many different values of h as they get closer and closer to 0, and seeing what the function reverts to. And you'll find that as you get very, very small values of h, a very small number squared is going to be even smaller, and so this term here is going to drop off the fastest. And what you're going to be left with is 2hx over h, and so the h's are going to cancel, and you're left with 2x. And so f of the derivative of x squared is going to be equal to 2x. But you don't have to do this for every single function, which is really handy. And a lot of mathematicians have spent years going through many different functions and working out what the derivative of those functions are, basically what the slope of those functions are at any point, and that's very, very helpful. And so instead of memorizing, going through this here, this big process to find out what the derivative of x squared is, we just know the simple rule that if you have something polynomial to the nth power, then the derivative dx to the n with respect to x is going to be n. So you times whatever's in the exponent by x, and then you subtract 1 off the exponent. And so this is really easy. In this case, we've got x squared over we've got x squared, and we take the derivative of that with respect to x, and what we get is 2, which is our n going out the front, 2 x to the power of 2 minus 1, and 2 minus 1 is going to be 1, and so we've got x to the 1, which is just x, and so that's equal to 2x. And so we've got lots and lots of different rules that can help us to we don't have to know all of this and go through the whole process. We can just shortcut that. So a few other ones that you'll probably want to know. This is the one for exponents or polynomials. Other one you probably want to know is if you take the derivative of a sine function, you get a cos function. If you take the derivative of cos, you get minus sine. And if you look at the plots of sine and cos, you can see how this comes about. Probably my favourite function at the moment is the exponent. The exponential function, e to the x. And if you take the derivative of e to the x with respect to x, you get e to the x. Isn't that great? So you don't even need to think about this one. This is great, and this makes sense as to why we use it so much in physics and also in chemistry, because if we take the derivative of this, we find that it's e to the x, and this sort of is kind of like the this is the definition, I guess, of it. We chose a function that is its own derivative, and that makes a lot of our calculations very, very, very easy. Something else I wanted to show you with this is that if you have the exponential function, we found earlier that you can actually expand this as a Taylor series, and you get out 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. And we found that if you were to have a complex exponential, then you'd actually get a cos, and you'd also get an I times sine. But if you actually look at this is a whole series of polynomials. And we know the rule for differentiating polynomials, which is x to the n, will go to nx n minus 1. That's our rule for differentiating polynomials. So what you actually find is if you take the derivative of this, this here has no x component, so it will go to 0. If you take the derivative of x, you'll get 1 out the front. That's our rule for polynomials. X, and you'll get 1 minus 1, so this will be x to the 0. X to the 0 is 1, and so you get plus 1. And you'll find that what you get from this here is you'll get 2x is actually divided by 2 factorial. And you can see that as you go through this, you're going to actually end up with 1 plus x squared on 2 factorial plus x cubed over 3 factorial. And so you actually get back exactly the same function. And so this is kind of one way of seeing how the derivative of the exponential function is itself an exponential function, because basically what happens is that each time you take the derivative, you're just moving one step down this this chain of polynomials, and you get out exactly the same values. So so that's all I wanted to show you, and I'd suggest looking at the list that I gave you of some common differentiation derivatives that you'll need to take.